Hello class, and welcome to Module 3, Part 1. In this module, we'll be talking about confidence intervals. Our objectives today are to introduce and define the t-distribution, define population parameters and point estimates, and define and calculate a confidence interval. So, in Module 2, we talked about normal distribution. Okay, so if you recall normal distribution, you can either have an x or a z variable. The x stands for your normal variable. Your z is the standard normal variable. They both have a bell-shaped curve, which means 50% of your data lies to the right, 50% of your data lies to the left. It is symmetric. The big difference between the two was with your z score, okay, the mean is always 0 and your standard deviation is 1. And with your normal variable x, you're given your mean and you're given your standard deviation. Okay, so t-distribution. The t-distribution is a family of distributions that look almost identical to the normal distribution curve, only a bit fatter and shorter. The layout of the distribution depends on the sample size. So for sample size, we use the variable n. And an example of a sample size would be if I wanted to collect data at a high school, there were 1,000 students, my sample size would be n equals 1,000. So the t-distribution can be used to calculate probabilities for small samples or when the population standard deviation sigma is unknown. So again here, just looking, this is just a little bit shorter and a little bit fatter than a bell curve. Okay. So let's go over here to the t-distribution. Okay, so just like your normal distribution, we have function in Excel to help us calculate the probability of a t-statistic and vice versa. So remember, vice versa just means we need to find the inverse. So if I need to find the probability of a t-statistic, I'm going to use this formula right here in Excel. And this DF, this stands for your degrees of freedom, which we'll talk about in a little bit. And again, that's always got to be true. Key thing here, this is only for left-tailed values. Okay. If you're finding the t-statistic given a probability, we want to use this one here because we're going to do the inverse, so the opposite of the other equation here. And again, notating this is only for left-tailed values. Okay, just like what we talked about with the other things. Some vocab for you to learn. A population parameter is any summary number, like an average or percentage, that describes the entire population. For example, one population parameter is mu, which represents the population mean. The problem is that most of the time we don't know the real value of the population parameter unless we have a census. So the best we can do is estimate. So for example, if I wanted to find the average height of men in New York City, I'm not going to go door to door and ask for every man's height. I'm going to go and I'm going to take a sample, maybe a sample of each neighborhood bureau, and then make my determinations from there. I'm not going to actually go and measure every single male in New York City. Okay, so a point estimate of a population parameter is a single value of a statistic. For example, the sample mean, and how I say that is x bar, is the point estimate of the population mean, mu. Okay, so just kind of what I was talking about here. Let's say we want to know something about a population. Okay, we're going to take a random selection. That's called a sample with what we want to work with. And the sample mean is x bar. If I wanted to find the population mean, that is going to be mu. But generally speaking, anytime we're dealing with statistics, we're looking at that sample. Okay, so just some notation for you guys to look at. Okay, so if I'm talking about population, and it's going to be really hard to see the difference between these two, but if I'm looking for proportion, the population parameter, that's going to be pronounced as rho. With the sample statistic, that's just p, and we call it a hat, so p hat. If I'm talking about the mean, so the population mean is going to be mu, and for the sample, that is x bar. When I'm talking about standard deviation, if I'm talking about the standard deviation of a population, that's sigma. And if I'm talking about the standard deviation of a sample, that is just S. You do need to know the difference between the two. Okay, so when I'm talking about standard deviation, whether I give you sigma or S, you do need to know if I'm talking about population or sample. Okay, so confidence intervals, what are those? Confidence intervals give us a range of values that we can be sure that a population parameter falls into a certain range, giving a point estimate. In other words, confidence intervals give us a range of values we are fairly sure our true value lies in. So again, you're looking at a sample and we find the mean. Okay, so we find the S. What I'm looking for, though, I want to know with the confidence, how likely is the population mean going to fall? How close is it going to be to our sample mean? Okay, so we give confidence intervals. Typically, our confidence intervals are 95, 99, or 90%. So why do we need confidence intervals? Since we are only working with a sample, researchers need a way to measure how well the sample represents the population. The probability that the confidence interval includes the true mean a population is called the confidence level. Okay, so let's look here. So a confidence interval consists of 3 parts. So like I was talking about, the common levels are 90%, 95, or 99%. A sample statistic, aka that's my point estimate. So you have x bar, S, or that little p hat, things we were talking about. So mean, standard deviation, okay, or proportion. Your margin of error, this is how far away your values can differ from the sample statistic. Okay, and we're going to talk about how we find all of those in just a second. Okay, so here is an example. So let's say we measure the heights of 40 randomly chosen men and get a mean height of 175 centimeters. We also know the standard deviation of men's heights is 20 centimeters. Okay, so let's say I want to have a 90% or a 95% confidence interval is 175 centimeters plus or minus 6.2. Again, just making sure we look at the correct notation here. Since this is a mean height of 175, since we're talking about the sample, I would use x bar. And the standard deviation, again, of the sample, I'm going to use S is 20. Okay, so those are things to keep in mind. This plus or minus 6.2, that is, okay, that's what I'm talking about with my confidence interval, because 175 is the mean we have. So I'm saying the 95% confidence interval is 175 plus or minus 6.2. So I'm 95% confident that the true mean, so the population mean, lies within those values. So 168.8 to 181.2. Again, just reiterating here, this says that the true mean of all men, if we can measure all their heights, is likely to be 168 centimeters to 181.2. A word of caution, it might not be. Remember, this is 95% confidence. So the 95% says that 95% of experiments, like we just did, will include the true mean, but 5% of experiments that we run would not. Okay, so just keep that in mind. Okay, so we're going to concentrate on estimating the population mean and how to calculate the confidence interval for mu. Okay, so you have your x bar. So again, that is your mean in a sample minus E, which is how we're going to figure out that's, okay, my margin of error. And mu is that population mean. Okay, so x minus E, x plus E. Okay, so in order to find confidence intervals, the first thing I need to do is find the critical value. Then I need to calculate the margin of error. I'm going to add and subtract the margin of error from the mean, and then I'm going to interpret the confidence interval. So there's a 95% chance that the confidence interval, okay, contains the true population mean, and there I would introduce or insert the confidence interval. Okay, so let's look here. So how do I actually calculate the critical value? So that's going to be our step 1 to solving all of this. Okay, and the notation for that is t sub alpha divided by 2. So first thing we're going to do is we're going to calculate the degrees of freedom. So that's what that df is, and that's always your sample size minus 1. The next thing I want to do is I need to compute alpha. So that's 1 minus your confidence level divided by 100. And really what that confidence level divided by 100 is, you're taking that percent and you're turning it into a decimal and subtracting it from 1. Okay? And then I'm going to go to Excel and type this in. Okay. Okay, so why don't you go ahead and I'm going to pause this video and I'm going to come back